What is up, students? Let's take a little time today to learn about mining ore. All right, so you did some reading yesterday where we learned a lot about the mineral resources that we have available to us in Minnesota. And one of those things that was discussed was something called iron ore or taconite. And some of you asked the question of how do we get from all mining that stuff? What does it do? Where does it go? How does it work? And that's kind of what today is all about. So let's dig into it. See what I did there? Dig into it. Sorry. All right, anyway, let's start by defining the word ore. So ore is rock with a specific mineral deposit, such as metals that can be removed specifically for profit. All right, so if we're looking at these pictures here, let's do it where I have the fun pointer. There it is. Sorry. All right, so if we're looking at this top picture is aluminum ore. In the middle, we have iron ore, which we mine a lot of in the state of Minnesota. And at the bottom, we have copper ore, which we will learn a little bit more as we go through. All right. So the question is, how are ores made? And essentially, you guys, there's three ways that you can get an ore. You can get it from the cooling of magma. You can get it from something called contact metamorphism. Or you can get it because water somehow contributes to it, moves through rock, steams through rock. We'll talk more about that in just a second. But let's go ahead and start with the idea of cooling magma. Now, this is what you guys know. Magma is liquid rock. And rock is a mixture of all kinds of different minerals and elements and other stuff that's been melted. And it's kind of this cool, soupy mess of minerals and materials. Okay. So here we are. We have this represents magma underground. And like I said, it's liquid and it's got lots of different mixtures in it. It's kind of a homogeneous mixture to go back to what we learned about earlier in the year. All right, so here we have this liquid magma. And as it starts to cool, certain minerals will start to come out and solidify faster than others. That has to do with how quickly they cool or their cooling temperature, their freezing temperature, if you will. Now, because of gravity, the heavy stuff will fall towards the bottom because it has a greater density than the magma. Oh, yeah, density, it's back. The stuff, other stuff, you guys, is held in suspension or it floats within the magma because it's not as dense as the magma, so it floats. See, density. So what happens is that these crystals start to concentrate together. So it can be crystal, it can be the mineral iron, it can be the mineral copper, whatever, but it starts to sort of concentrate in the lower parts of the magma. And then when this entire thing becomes solid, you have this rock with a high concentration of a particular mineral or several minerals, depending on their density, okay? So let's talk about ore from contact metamorphism. So as you guys know, if we're dealing with a metamorphic rocks are made when we apply heat and or pressure to existing rock. So here we have, again, this represents a big chamber of magma underground. It's hot! Okay, this is all liquidy stuff in here. Now, this rock that surrounds the magma chamber, this is still solid rock. It's just that it's really hot because it's in contact with this magma chamber right here. So what happens in this area where it's kind of a lighter orange, this is what we call a contact metamorphic area or contact metamorphic zone, where it's hot enough to chemically change the rock, but it's not so hot that it melts the rock back into magma, starting the igneous process again. So your ore forms where the magma touches this rock, the temperature changes and the pressure changes in this area cause the rock to chemically change, and we end up with some sort of ore as a result of that. Again, a concentration of a particular type of mineral or element. So far, so good? Excellent. All right, let's talk about the third way we can get an ore, which is ores from water solutions. All right, these are what we call placer deposits. And the way placer deposits work, essentially, all right, so this is a riverbed, okay? Look, it's a waterfall. Water is the greatest solvent on the planet. It means it can pretty much dissolve anything. Sometimes it dissolves things quickly, like if you put some water in your hot cocoa powder and then it dissolves, or it can take a really long time for water to dissolve something. For instance, water dissolving rock takes a really long time. But if your rock happens to be full, like in this, let's say this cliff or this area down here or here happens to be full of a particular mineral or metal or whatever, water flowing over and over and over again at high speeds creates a lot of energy, and as a result, it starts to carry these things down to the bottom of our waterfall, or if it's a little bit lighter, it starts to dump it over here. Because remember when we talked about sedimentary rock a few weeks ago, we talked about the fact that different sizes of sediment tend to sink or tend to float a little bit longer or get carried farther. That's what we see in riverbeds. We have these deposits that end up getting buried over time. Look, there they are. They're buried, and these are called placer deposits. And if you can find them, then you can make money off that. You can mine those placer deposits. And when you see people panning for gold, that's essentially what they're doing. They're looking for those deposits in stream beds. All right, let's talk about ores from water solutions. So we're still talking about the water thing. Like I said, there's a couple ways that this can happen. Placer deposits are one. The other is if we have hot water moving with pressure through cracks in rock. So let's look at something here. Look, it's magma. Magma's hot. Because of the heat of this magma, the heat and the pressure causes the rock above it to crack and buckle and move and bend. It's a pretty violent process. And when that happens, if there's any water trapped in these rocks, where does it go? It goes up because of the pressure. And again, water, when it's moving really fast, it dissolves rock. And as a result of that, anything, you can see these veins right here. These veins of gold, you guys, are the result of gold being forced through these cracks because of hot water, carrying that at high speeds. Eventually this will cool, eventually the water will slow down, and then eventually you get these big veiny deposits where water carrying gold move through, then the water's gone, it leaves the gold behind. And so a lot of times when people are, you hear them talking about veins of gold or veins of a deposit, this is exactly what they're talking about. Something that has been deposited through cracks in rock, through high pressure heated water. It's pretty cool. I think it's cool. All right, so all of this, now the question is, how do we go out and get this stuff? How do we go, because, you know, that's the cool thing about the ore industry is that it's a big money industry, billions of dollars. I'm going to say that more than once, just so you know that. So how do we obtain this ore? Well, there's several steps. Number one, you have to prospect it. So what you do is you look at the deposits on top, you have some ideas based on what the geology looks like, and then you start drilling down and you start prospecting. Prospecting means that you're going and looking. What you see in this picture are what we call core samples. So you have a drill with a big hole in it, and it drills down, and it drills down hundreds of feet, and then they pull that drill up, and inside that big hollow tube that they drilled down with is a core of rock. And so now what geologists do is they literally just go through with a fine-tooth comb and all their instruments and all their little microscopes, and they go through and they figure out what the rock is made of. And if it looks like they could end up finding some really valuable minerals in there, then they start to do this. They start to mine it. There's lots of different ways you can mine. You can strip mine, you can open pit mine, you can shaft mine. So a strip mine, you guys, tend to be wider and more shallow, closer to the surface, where they just basically strip stuff off the side, strip stuff from the bottom, and then they have these series of, these tiers you see are essentially roads that will A, allow you to strip the sides, and B, allow you to drive out of it. Same thing kind of with what you see here, open pit mines. Open pit mines tend to be much deeper and on a much grander scale. I've actually been to an open pit mine in Colorado, and it's massive. They're actually mining for gold there. And it's a little bit terrifying because you see just the destruction that is wrought on land when you see strip and open pit mines. It's not pretty. And then finally, when our mineral deposits are too deep to get to from open pit or strip mining, we actually drill what are called shaft mines, which means that allows you to transport yourself deep within a rock bed. You see this a lot in mountains. You take a train down there, you work down there, and they basically use a system of conveyors and trains to get the stuff from deep within Earth's crust to the surface. Okay, that's kind of a lot of people's vision of a mine is a shaft mine. Okay, so the third step is what we call the smelting process. And this is where things get a little bit complicated. So essentially what you're doing at this point is that you're, instead of, going out and digging up all this stuff, now you have to put your other skills, your chemistry skills to work, your understanding of minerals, your understanding of chemistry, your understanding of elements in order to separate the good stuff, the stuff you really want, the iron, the aluminum, or the copper, from the stuff, the other waste products. Because when this stuff is in the ground, it's not just pure. You have to separate the bad stuff from the stuff you want, and that's the smelting process. Now, like I said, this process is a little bit hard to explain. So here is a really excellent video that's going to show you the process from all the way from the beginning, from figuring out it's there, from mining it out of the ground, and then from processing it in order to get, in this case, nearly 100% pure copper. Let's have a look.
Have you ever wondered what your life would be like without copper? Don't worry, it's not something most people spend a lot of time thinking about. But the fact is that without this basic element, you'd be stuck with no running water, no phone, no computer, and no electricity for that matter. In other words, without copper, your life would be downright primitive. So now that you know how important copper is, let's talk about how it's made. Or to be more accurate, let's talk about how it goes from this, a basic element mixed in with a bunch of other minerals and garden variety rock, to this, 99.99% pure copper cathodes manufacturers use to make that long list of stuff you depend on every day. The whole process starts with monster machines and high explosives. At the Bingham Canyon mine, teams of blasting experts drill 12-inch diameter holes 56 feet into solid rock, fill the holes with about 1,200 pounds of high explosives, and boom! Solid rock instantly becomes loose rock. In fact, every single day, blasting crews drill and blast about 160 of these holes to create 500,000 tons of new blasted ore. So exactly how much is 500,000 tons? Well, a humpback whale, one of the world's largest animals, weighs about 50 tons, which means you'd need about 10,000 of them to balance the scales. So how does Kennecott deal with this nearly inconceivable volume of blasted rock? Well, the simple answer is that you pick it up with giant shovels that can carry 100 tons in a single scoop and dump it into massive haulers. These trucks are capable of hauling 320 tons, or about 6 whales, and are about the same size as an average 2-story house. These huge hauling machines carry the blasted rock, which contains minerals called ore, out of the mine and drop it into one of the world's largest rock crushers. This giant crusher turns the big car-sized chunks of loose ore into more manageable, basketball-sized rocks at the rate of about 10,000 tons per hour, and then drops the crushed ore onto a conveyor belt. The conveyor system, which is basically a giant moving sidewalk for rocks, carries the ore through a 3-mile tunnel, then continues up hills, down hills, and past 6 transfer stations until it reaches the Kennecott grinding facility. This 5-mile trip takes about 29 minutes. If only rocks could appreciate the fun of traveling 5 miles on a moving sidewalk. When it reaches the grinding facility, the ore runs through a series of giant rotating mills. This grinds the basketball-sized rocks into a fine powder. After all that blasting, hauling, crushing, conveying, and grinding, the copper is finally ready to be separated from all the other minerals and materials that surround it. This is also where the process switches from brute force to applied chemistry. The finely ground ore is poured into flotation cells and mixed with exactly the right amounts of water, air, and chemicals. This causes all of the copper-bearing minerals to cling to air bubbles and take a free ride to the top of the flotation cell. The result is a liquid material called copper concentrate, which is now about 28% pure copper. This concentrate is pumped 17 miles through a long pipe to a filtering facility and dumped into a big storage tank. At the filtering plant, the concentrate is pressed, filtered, and dried in a massive rotating dryer. After it's done, the material looks a lot like coffee grounds. This powder goes into a large, very hot flash furnace, which causes the dried concentrate to melt and turn into a molten metal called matte copper. During this process, sulfur gases burn off and are then captured and cleaned. A combination of iron and silica rises to the top, and the heavier copper matte sinks to the bottom. This matte, which is now about 70% pure copper, is collected, cooled, and sent through yet another series of furnaces. This burns off most of the remaining impurities and leaves us with molten copper that's about 99% pure. This nearly pure copper is poured into 700-pound copper plates called anodes and left to cool. 99% pure copper is good, but getting to 99.99% takes a little extra molecular mojo. The anodes are shipped to a final tank house facility, where they're sandwiched between stainless steel plates and loaded into big square tanks that are designed to conduct electricity. The tanks are filled with an electrolytic solution that creates positive and negative electrical currents, just like the world's biggest car battery. This current causes the pure copper ions to jump to the stainless steel plates. It's a pretty strong attraction. The result is a 99.99% pure copper cathode. These cathodes are stripped away from the stainless steel plates, corrugated, strapped together into 5,000-pound bundles, and whisked away to their final destinations. And finally, they're turned into cell phones, computer components, copper pipes, copper wire, and many other things that make our modern lives possible. That's the amazing story of how we take copper from this to this. 99.99% pure copper. It's not easy, but when you stop and think about what our lives would be like without copper, it's worth it.
Okay, so like I said, the process is a little bit complicated, but make no mistake about it, ladies and gentlemen. The reason we spend time talking about rocks and minerals in 8th grade science class is because you need to understand that this is a multi-billion-dollar industry, and that the modern and enjoyable life that we have is a result of rocks and minerals and the processing of them in order to build and give us the things that we like and enjoy. And people make a lot of money doing this. Like I said, this is a multi-billion-dollar industry. So the next time you pick up a rock or somebody dismisses a rock like, ugh, it's just a rock, remember, we can't exist on this planet without rocks. And B, the modern conveniences that we have are found within those rocks. So here's some of the equipment. This is Miss Wilms, and she got a chance to do, I can't remember which mining operation she was at, but so when in the video when they showed you those massive haulers, that's how they are compared to a person, okay? These are the buckets. These are these massive pieces of equipment. Again, you're looking at what's essentially a strip mine or an open mine operation here and here. So yeah, like I said, a lot of time, a lot of effort, and a lot of money goes into to these resources because what comes out of the ground is so amazingly valuable. All right, that's it. Everything you need to know. Well, maybe not everything, but a lot that you now know about the mining industry.